I'm Francis Buontempo, but you can just call me Fran if you want. I'm going to ask 2 questions this morning. What is a random number, and why should I care? Well, you can search the internet and find a variety of random numbers. Comments from a Stack Overflow question claiming 59. There's a random number. So, we're only a few seconds in, and I think we're on the verge of having dealt with the first question already. There's no such thing as a random number. Right? Tick, halfway there already. Why is that? Well, if you've got one number, or object, or string, or whatever, or dice roll, you can't tell if that in and of itself is actually random. If I toss a coin, and I keep getting heads, I might start suspecting that it's an unfair coin and isn't giving me a random result of heads or tails. But on a single toss, no. So, question 1, what is a random number? Nonsense, no such thing, fine. So let's extend this out a bit. We can have a sequence of numbers that might be random. So there's never a single random number, but there might be a sequence of things that appears to be random. Which means, well, that's what we're going to try and dig into over the next hour partially. And, plot spoiler, I'm still not sure what random really means. So if anyone wants to keep discussing this with me, then that might be quite interesting, but that's for offline, I think. If you've got a sequence that appears to be random, whatever random means, it might still have properties. You might expect the average to be 0 or something like that. You might expect a certain variance. So you might expect everything to be near 0 and very unlikely to be plus or minus 1. Or you might have sequence of numbers 1, 2, 3, 4, 5, 6 if you're simulating rolling a dice, and then you might want each of them to be equally likely. So we can have properties of seemingly random events. I think sometimes people use the word random interchangeably with chaotic, and those are 2 fundamentally different ideas. Chaotic systems are precisely defined, but the trick with them is we often don't know all the initial conditions, and we'll briefly touch on chaos on the way through to see how it's different. I'm going to spend an amount of time talking about pseudo-random numbers this morning, just to remind us how they work and how we generate them on computers, mainly to avoid having to define what random really is. So there might be a little bit of multiplying going on and some modulo arithmetic, but it's 9 o'clock in the morning, so I've got the slides and I've already done the sum, so we don't have to concentrate too much. Now, if you've got a sequence, how do you know if that's actually random or not? If something generated the number 9 over and over, well, all you can say is, up to now, I can see a pattern. I know what's happened up to now. Don't necessarily know what's going to happen next. So random's partly about being able to, if I can spot a pattern, I can say, I don't think that is random. I can see this pattern going on. Now, in the future, something might change, and predicting the future's impossible to a point. Or you might have a sequence that isn't just 9s and go, yeah, I can't see a pattern there. So maybe random just means I can't see a pattern, but maybe someone else will, or maybe with some more information there is actually a pattern there. So I've still not defined random very well, but we're a bit closer. We're saying, no, I can see a pattern. Maybe I could write a function that returned 9 each time, and then that would emulate what this was doing. So if I can write a function that returns the same sequence, then it's probably not random. And yet that's exactly what we do with our pseudo-random number generators, and that's cool. If you go right back to early computing, and Kevlin, I think, used this quote as well. Someone's definitely used this quote over the last few days. What we're trying to do if we're trying to write simple games, card games or dice games or anything like that on a computer is generate something random from a function. I just said if we can write a function for something, that means it's not random. So we make pseudo-random numbers, which are definitely not random. But that's okay. They're pseudo-random, they look randomish. So that's, we walked around the first question. So one thing we've learnt so far this morning, there's no such thing as a random number. Tick. Next, why do we care? Well, there's a variety of reasons. People use random number generators in their language incorrectly. Sometimes the random number generators don't have the ideal properties we want. I've talked about card games and dice games and similar, and even more powerful games. A bit of randomness makes it more interesting, more fun. Why do I care? Random numbers can make things fun. And you can do serious things with them as well. So I've spent an amount of time working in finance, and some of the financial instruments are so complicated you can't work out the result analytically. You can't do the maths to work out what something's worth. So you run a simulation. So you use lots of random numbers to try and work out on average what you expect to happen. And you can do the same if you're trying to model pandemic or any other disease spreading. Plug in some variables and see what might happen. And then you need to tinker with the variables to match reality more closely. And then you can attempt to predict the future, and you can actually work out what sort of things might improve situations. So simulating things can help you price things, help you save people's lives. Another thing I want to touch on is just a brief moment to think about how we test code. As soon as we've got random or pseudo-random numbers in our code, how do we go about testing them? I don't know if you've got some strong ideas on that. It might be a moment where we can share just briefly. And I said that the pseudo-random numbers have some properties we expect, so we'll briefly touch on what sort of things we want out of our random number generators. So, brief aside, another reason just to emphasise the point of why we care about random numbers. I've given a series of talks, I think over the last 10 years, looking back recently, I'm getting old, about how to code your way out of a paper bag. Which, I mean, can you code your way out of a paper bag? What does it even mean? I said I've given talks about this and I've got a signed certificate, so it must be true. Suppose I've got a brown paper bag. I don't think the colour matters, but why not? Suppose I've got some green blobs, and they all walk at the same pace, going up. No randomness, so we know exactly what's going to happen. We're going to demonstrate we've coded our way out of a paper bag. But that's really boring, right? If I add some randomness, even if it's pseudo-randomness, we can have a race going on, and, well, if we had a propensity to gambling, we could place bets on it. I pre-recorded the demos due to my laptop dying last time I tried to do this demo, so I know who's going to win, so don't place any bets. If we add some randomness there, it mixes things up and it makes things more exciting. So there's no such thing as a random number, and we care because it makes things more fun, and it can be really, really useful and save people's lives sometimes. So I've already answered my questions. That was quick. Let's dig into how we make these pseudo-random number generators. How do we generate random outcomes? I think, do anyone know languages other than just C++? Anyone use Python a little bit? A few. I've got some example questions in Python, but the point is to think about what sort of functions we're writing rather than the syntax. And C# as well, and R. Anyone used R? So R, okay, a bit. And if you're doing some math simulation stuff, that's often a good starting place. Each of them have got, most languages have got pseudo-random numbers available for you, but all of them have a slightly different interface. So if you're switching between various languages, it's really easy to get really confused really quickly. So for example, the C#'s random next, if I say 1, 7, is that going from 1 up to, but not including 7, or not? Has the random number generator been seeded or not? Do we understand what the idea of seeding means? So, and we'll have a reminder in a moment, but if you seed a random number generator, a pseudo-random number generator of a specific seed, you'll get the same numbers back out. With some caveats of, it's on your machine with the same version of the language, the same operating system. So 2 things to hold in your head whenever you're confronted with a new set of random numbers. Do you need to seed it or not? And is the range including the upper bound or not? Let's look under the hood. Yes, that is a car full of walnuts. I don't know, squirrels. Destructive. I'm not saying that random numbers are like loads of walnuts chucked under a car bonnet, but it looks a bit scrappy if you start looking at what's going on. But it's based on some number theory, which is a very strange and unique part of maths, that you don't necessarily find some nice general results. Each problem is a specific problem that you have to come out with new ways of doing things. How do you generate random numbers? Or these are not random because we know what's going to happen next. They're pseudo-random. The most basic way, which C's rand is based on, and we've been doing this since back in the 50s, is called a linear congruential generator. So, you take your seed, x1, say, or x0, depending on how you count, multiply it by something, a fixed constant, add a fixed constant, then do some modulo arithmetic. And people spotted at some point, actually, you got better properties from your pseudo-random number generators if you just did the multiplying, didn't do the adding up as well. So, take your seed, multiply it by a, that's this bit, start somewhere, multiply it by a number, do some modulo arithmetic, gives you the next number. And we tend to use, for very good reasons, prime numbers. And often Mersenne prime numbers, which are 2 to the power of a prime number, take 1, give us some really nice properties. I'll run through all the properties later on, but basic intuition, you want to be surprised by the next outcome. It'd be unexpected. It'd not keep giving you 9 back all the time, or 0 back, or 0, 1, 0, 1, 0, 1. So if we take a recurrence relation, that being the proper term for this, of start with a number, multiply it by something, do modulo arithmetic, gives you the next number. If you try it, and try this with pencil and paper at some point, if you choose m as prime, how we pick a gives us different properties. So if a is 7, we can get a full run of each of the possible numbers up to 11. We start with 1, and then if you do the maths, do your, what am I doing? 7 times 1 mod 11, well that's 7, and do it again, and do it again. Eventually you get back to 1. We already know what we're going to get after 1, so you get this cycle. You get all the digits. If you chose A was 5 instead, then you go back to 1 much more quickly and you don't get all the digits. So that choice of A makes a big difference. And I don't think there's any general ways of working out precisely which A to pick that's best, because there's some number theory there. You can say ones that won't work, and we're seeing an example where in C++, one of the early random numbers generators use one value of A And there was a long argument with some academics for about 5 years, and they went, all right, this is a better value of A, and got an academic paper out of it, because that's life. If you don't use a prime number, think through what happens. Well, if A divides into M, for example, if we took 4, you can see that this collapses down and sometimes stops on the same number. So, stick with prime numbers for M. And like I said, go and play with some of these on pencil and paper. You just start with a number, multiply by something, and choose a modulo. And you can get sequences that look random. Of course, if you know that's what's happening, then you've spotted the pattern. So it's definitely not random. But it's good enough for playing games with. So. Now, that's the simpler ones. Back last century, so 1998, people published a paper about a Mersenne twister, heard of? That tends to be the go-to random number generator in C++ nowadays, and has been in other languages. It was under the hood in some NumPy things and Python libraries and other things. But it's really great because it doesn't just use the previous value of x, it uses some bits from that one, some bits from the one before, some bits from the one before, which has a great property of if you start with 1, chug through, when you hit 1 again next time, the previous numbers will have been different, so you don't then get the next number, so that it takes way longer to cycle round. But it's got a large amount of state going on, which means you can't shovel it onto your graphics card and do GPU stuff there very easily, because it takes up a lot of space, but it takes much longer before it starts repeating. And there's loads of ways of generating random numbers. So we've just seen the linear congruential, zoomed through the Mersenne twister. If you just look in the C++ random header, or on a reputable website that talks through what's what, there are loads and loads of other engines in here. And there's some really interesting maths behind this. So there's several that, so the Fibonacci one uses the last 2 values and combines them. So that takes much less state, but then it does repeat more quickly. But it might give you a bit more than the linear congruential one. And you can mess around, you can discard some of it, you can shuffle things round. Those are all the engine adapters. So having picked an engine, you can then do other things with it to make it even more random. It's not random because you've defined precisely and procedurally what you're doing. But maybe that's a philosophical question. But this is a fascinating, huge topic. And we've only got 40 minutes or so left. So go away and look up the different engines. Invent one yourself and get an academic paper published. I mentioned about the value of A making a huge difference. Again, if you look in the C++ header, spot the naming that's happened here. I don't know whether it was called min stand rand 0 initially, but that's got the value of A of 16,807 that we saw when I just put the sums up that I couldn't face going through early in the morning. People said, no, well, this repeats too quickly, and there's certain numbers that never get out first, and this is absolutely terrible. This back and forth argument for 5 or so years. And then the people who'd invented it in the first place went, no, we found a much better value for A. And then that takes longer to start repeating and looks more random, whatever random means. So in the same header, we've got our min stand random without the 0 on the end, which just means it's using a different value of A. Interesting little history. I think for a long time we've settled on Mersenne twister do. Like I said, there are some caveats. If you want to do some GPU stuff, it takes much more state than the old school linear congruential things. And there does seem to be a proposal out there to introduce some different types of generators. So there's whether they come to pass or not, and they've been designed to try and have a much smaller footprint, so you could do some GPU stuff, but the similar property, if I see 1 and I see 1 again, it doesn't start immediately repeating, just gives you more unexpectedness. Don't know whether it's actually randomness. Yeah, I think Python's, some of you said you'd done some Python, that NumPy switch from using Mersenne twisters to yet another type of generator. So there's a surprising number of ways of generating things that appear to be random. Or at least you go, I can't easily spot the pattern, even though it's been coded up, so it got a pattern, so it's not random. Yeah, so some details about the proposal. And it's just basically making the point about it's taking up a lot of space. And there's some situations where you want something called quasi-random numbers. Anyone heard of? Okay. So pseudo-random numbers aren't random. They're generated by a program. And if you know what the seeds are, you can get the same sequence back out again. Quasi-random numbers are the same, but there'll be some situations, and I've seen this in finance, where if you're expecting a normal distribution, if you draw like plus 0.1, well, you want symmetric results in your simulation around the mean. So each time you get a plus 0.1, you want a minus 0.1 as well. So you generate these in pairs, and there are various ways. That's just with one sequence of numbers. If you're doing things in 2D space or 3D space, you might want equally likely places in space or certain distributions. So the quasi-random number generators will tend to return things in pairs. So if you get a plus x, you get minus x as well, or something like that. So we've got pseudo-random numbers, and this other thing about quasi-random numbers, which you could use some of the adapter engines to do things with, or you could write code yourself and go, well, I've just got plus 0.1 out of my engine, so I'm going to return plus 0.1, then minus 0.1, and then I'll draw the next one. So it's quite easy to write code around this yourself, but if the proposal were to come about, we'll be able to do this slightly more efficiently. So let's do some hardcore maths now. We've done some multiplying. We couldn't face adding up because it was too early in the morning, but we did do some modulo arithmetic. If we take a value of x and do x squared and then subtract 1, the starting value of x can make a huge difference. You can see if you start with 1, it pings down to 0 minus 1, 0 minus 1 very, very quickly. So if we start with 0, we know what's going to happen. If we take a quarter or a half, it takes longer to collapse down. Play with this on pencil and paper. If we did some magic, instead of varying the start number, let's start with 0. Let's keep it simple because it's early in the morning. If the number we subtract, if we investigate those, who knows where this is going? One or two hands. If you use a complex number there, I don't know if you remember or have used complex numbers before. If you haven't, fine. Just think of it a number with 2 parts so we can plot them like an x and a y. It's either going to cycle round, collapse down to something really quickly, or expand. So if we colour it black, if it collapses down, or give it various colours as if the number expands out of hand, we get the Mandelbrot set. And some of you knew where that was going, didn't you? You said that. Oh, actually, I said at the beginning, randomness and chaos were completely different. The point about this is that was a really simple equation we're just squaring a number and taking something. Slightly more hardcore than just multiplying by a constant, but not much more hardcore. But unless you know precisely what the value of C was to begin with, the nudge from a blue region into a black region is minuscule. I think Lorenz spotted this first when he was playing with modelling some weather conditions. He printed off the values as floating points up to 8 decimal places. Obviously there were a few more in the computer as it was running the simulation. And then when he turned it on again the next morning and typed in that slightly less precise starting number, this tiny change, this butterfly effect, gave totally different results out of the weather simulation. So a tiny change in the start value in the deterministic formula gives you mind-blowing chaos. But that's not the same as random. But it's a bit like our pseudo-random stuff, because it's not random. I said, I don't know what random means anymore, and perhaps you'll all come out of this going, oh yeah, I haven't got a clue either, which is fair. And you can go crazy, you can multiply x squared by 2 and then see what happens. For some of the cryptographic random number generators, some of what they're doing is something squared multiplied by something, so much more hardcore than what we're doing this morning. We're not going to square anything, just multiplying and modulo. We play with some of these recurrence relations and get loads of interesting things going on. How do we use them? Well, yes, badly. I've got a hammer, bash, whoops. Let's have a little think together. How are we doing for time? About halfway. So we've talked about seeds. We know for the linear congruential one, that's the first value of x. And then that gives us the following ones. And though the Mersenne twist is far more complicated, you can give it a seed or a sequence of seeds because it's got all this state, like I said. So what do you use to seed it? Some people say, no, I've got a sequence of regression tests for the stuff I've got random numbers around, and I just use a known seed. Anyone do that? I mean, that's quite a common thing for people to do. You might find that on different operating systems, you get different sequence of numbers out. You might find if you upgrade your compiler, you need to rebase all your regression tests. If you've set them up well, that shouldn't be a problem, shouldn't be difficult, but using the same seed will give you the same sequence of numbers under some certain circumstances, so just be aware. I've been reading through and reviewing several books recently, particularly for Manning publishers, and noticed loads of people say, for some machine learning stuff, loads of people said, oh, I use this seed, then I get this. I'm like, you haven't told me which version of Pandas or Python or C++ you're using, and I've got totally different numbers, and I'm not surprised, but we usually do say what seed we use, but you need to give more information than that if you're trying to give someone a repeatable experiment. Say, like, what version, what operating system, just a bit more than just the seed. Threads can make things really confusing, right? If you've got a random number generator and you've got several threads drawing from it, you don't necessarily know which one's going to get which number next. But I mean, that might make things look even more random or surprising or unpredictable. And if you're trying to use C's rand, then you're going to potentially get in a mess. So I suggest you don't. Maybe if you're doing C++, don't drop down to C. Use C++ random instead. Some of you said you knew some Python. If you don't, it's fine. Suppose I want to roll a dice in any language. I'm going to have to include my random library. And I gave us 2 questions to concentrate on earlier on. So, in Python, it uses something like the current time, I think. Could be wrong, to seed things. So if I was to run this program twice, I might get a different outcome. And also, is the range half open or closed? Well, Python's got two ways of asking for a random integer. One is the closed range, so when I say randint 1, 6, I get numbers 1 up to 6 inclusive, and they're all equally likely. But it's got a rand range as well, which is half open, so then I need to say 1 to 7. So watch out for the boundaries, and do I need this to give potentially a different outcome each time or not? Is it seeded or not? If you use C's rand, which I wouldn't do anymore because I have to think too hard, it's really easy to go, oh, well, surely if I just get the number back, having seeded it with the time or something, and do modulus 6, then I'm simulating rolling a dice. The trouble is, up to rand max, I might not have precisely the same number of numbers in each of the 6 buckets. So I've skewed the distribution if I do that. Now, it's not beyond the wit of man or woman to go for the formula at the bottom, but you're going to have to concentrate on working that out. Whereas, I've just seen in Python, you can easily ask for a number between 1 and 6. And with the uniform integers in C++, you can say, I want it between 1 and 6, and it'll do the right thing for you. If you see anyone suggesting, if you want equally likely number between 1 and 6, or 1 and 10, use modulus, rant away, because you're going to make one of those numbers, or more, less likely, unless you've got really lucky with your number of buckets you want to carve things up into. So if you see modulus signs going on around using random numbers, possibly a bit of a code smell, might not be, but in most cases people don't know what they're doing, which is fine. Let's help each other out. But if your language does things properly for you, then use that rather than doing it yourself. So let's roll a die in C++. Anyone use the C++ random library that was introduced years ago? So, hash include random. You can ask for a default random engine that's probably the Mersenne twister that we touched on briefly. And we can ask for a uniform int distribution using numbers between 1 and 6 inclusive. There's a uniform double distribution that is half open, but that's because doubles are quite, let's just roll dice, easier, much easier. And then, so we've got to have two things. We have the generator, which does something like C's rand for us, but if it's a Mersenne twister, it might get some stuff, and some other stuff. And then we want a distribution, which is a mathematical function, or another way to put it, it buckets things up for us, smears them out with maths rather than magic. That would give us a number between 1 and 6. We pass the generator to the distribution, get our next number. Is this code good? 2 questions. Is it inclusive, half open, or up to the 6? Yes, we've talked through that. What was the other question? Seed. So if I run this twice on the same operating system with the same compiler, I'm going to get the same numbers because I've forgotten to say use a seed. Python will seed things for you, and so will some other languages. C and C++ will give you the same thing each time on the same compiler, on the same OS, unless you give it a seed. So that means you need to find something random, but we don't know what random is, to kick off the random. So the default random engine is probably the Mersenne twister, which takes all these bits of state, and whether it's 32-bit or 64-bit and so on, which has got a default seed. I don't think the standard dictates precisely which number it is, but that I think I've found that in probably a Visual Studio. And then it seeds it with this 5489 for us, which gives us the same numbers each time. So, what we want to do is add a third line. You can use random device, and you can call that, and it will give you a random number back. Except on some older versions of Visual Studio, where, well, there's no such thing as a random number, right? Some early versions of Visual Studio always gave you 0 back, which might be a random number, but in terms of what we're trying to achieve, it's not much use. Newer versions of Visual Studio don't do that. In theory, it's looking at the entropy on your hard drive. We're trying to define entropy in about 10 minutes, and then we're nearly done. So, but if you do, so 2 things: seed it and just pay attention to whether you're getting it upper bound or not. Also notice, and we know this, don't we? That's a template, the uniform int distribution. I don't need to actually specify int or unsigned. It can use the parameters to deduce the type. Yeah? Yeah, cool. So, seed things. And the random device will probably work nowadays on most things. You could pick your own random number, like 0, and then you might get the same thing each time. You could use time as well. A lot of people used to do that. That's okay. I did that once in some of my coding my way out of a paper bag thing. I set up 5 generators, seeded with the time, in a type for loop. Guess what happened? They all got the same times. They all generated the same number, so all my blobs did the same thing. So it was really boring. And I said random numbers are meant to make things more interesting. So just time works, but don't seed several generators with the same value because they're doing the same thing. Don't know if anyone's seen some of the discussions out there about people ranting about Mersenne Twister being absolutely terrible, not only using this huge amount of state, being really, really hard to seed. Well, it's not. We saw the header just picked on the 5,000 and something, shoved a number in. What's all the drama about? And we've random device, seed the engine. Bosh. No. Some papers saying this is severely flawed. And this is actually true. If we give a 32-bit number, we're only going to get a small percentage of the number of possible initial states. If we're just rolling some dice or playing a card game, that's not really going to make much difference. If you wanted to run a Monte Carlo simulation to work out how COVID was going to spread or price a financial instrument, you might have an embarrassingly parallel problem in places, so be able to spawn off thousands of different processes on some server farm. And then you might end up with some of your simulations ending up doing the same thing. But that's quite a niche problem. So I think severely flawed is slightly emotive language, but if you just seed it with one number, you're going to miss out on some potential first numbers. Probably doesn't matter if you're just writing games, but there is some number theory and probability in the background here. So, you can play around with this. There are actually 2 ways of seeding Mersenne Twister. You can just bosh one number at it, or you can give it what's called a seed sequence, and it'll go through the sequence and fit in the previous X numbers, because we said the Mersenne Twister uses the last one, the one before, and actually quite a few of them, and that's what all the letters in the template were for defining it. So you can use a sequence. If you use a seed sequence, then you can never, ever get 7 or 13 as the first number. And you can prove that with maths. Hands up if you care. 1. if you care, someone cared, and that's all right, that was a rant about seed sequence. If you desperately, desperately want to get the number 7 out of your random number generator, if you don't use the seed sequence, and that seed sequence you could do a comma and give it some other numbers. If you give that same number just straight as a number rather than a sequence, just specially for you, that generates 7. Happy? Hey! Basically, there's 2 ways of seeding it. If you're just writing some little games and things, this is fine. If you're doing lots of simulations, like I said, several thousands of processes on a server farm, well, actually, possibly you need to start writing your own random number libraries and things, or resort to some adapters to make sure you get the variance you're after. But you can get 7 out of it, just not with the seed sequence. And if we're going for democracy, we don't seem to care, really. Some people have suggested, well, if I can't get 7 out of it, maybe I should do a warm-up. And an academic paper about this, which is awesome. Well, first, I think the academic paper wrote a for loop to chuck all the things out that they didn't want and used a random number to decide how much. And then you've got a bootstrapping problem of, I really don't think random means anything. Anyway, the C++ allows us to discard a certain number, so you can write academic papers about anything, and I've written a few, so I should know. Also, if you dig in through what's actually happening, the seed sequence does go through each of the seeds, so it is sort of doing a warm-up for us. Right, if we just give it one number, it doesn't do that warm-up thing, but if you give it a sequence, it will chug through a few of them. But look, this is huge. There's a lot of discussion out there in academic papers and on the internet about percent twister's awful because no one knows how to seed it. We do. Call random device. Good enough. You might even get 7 or 13 as the first number. If you don't, you can use seed sequence. You might, well, you won't get 7 or 13, but other numbers are available, and if it's doing the maths properly for us when we use the distribution part, you won't notice. Right, back to thinking about simple things. Rolling 2 dice. 2 generators or 1 generator? 2? 1? Yeah. You could have 2 if you wanted. But 1's probably alright. I can see some circumstances where if you did, like, hit 2 to the 32, repeat on things, then you might end up with the same game, keep playing. But if someone's played a dice game that long, they've got a gambling problem rather than anything else. If I did the same thing in C++, so the Python code got 2 generators, rather than just calling random in directly, that's what I was saying about if you use time there, one, then the other, the chances are you're going to get the same sequence out. Pick a card. Well, you could use 1 to 52 and represent individual cards. Same questions as usual. Always think about those 2 questions. Probably want to shuffle the cards first. If you start shuffling things, there's certain problems that crop up surprisingly quickly because this ends up being a combinatorial problem. So if you were trying to do some kind of DNA sequencing or something, well, now we're budging it up against algorithms. Does this shuffle work? If you were to write shuffle from hand and you want to shuffle 3 cards, pick one, pick another one, swap, then pick another one, swap, then pick another one, swap. pick one of three, and then pick one of three, and then pick one of three, you've done 27 possible things. But if you think it through, there's only supposed to be 6 combinations, right? So basically, unless you really know what you're doing, look things up or use things in your language's library. If you pick one card and then disclude that and then shuffle the remaining ones, you walk backwards, you don't end up moving things backwards and forwards and you get the right number of combinations. Unfortunately, C++ has a random shuffle. Well, it had a random shuffle, and Kevlin moaned loads in his keynote about that disappearing. Some implementations use C's rand for that. And I told you, be very wary of modular of percent going on, because that you might not be able to divvy things up equally. So that's been deprecated because it's terrible and you couldn't seed it directly. You had to use C's rand, and then you've got problems with threads. Which leaves us with standard shuffle. And again, we need to give that some kind of generator. So you need an extra line or two of code, but it's not a disaster. And here we haven't got that inclusive, exclusive range to think about. We just go shuffle this collection. By the way, here's the generator. If we're going to choose, well, you can choose like 3 by picking 1, 2, 3, so you don't replace them, or pick one, put it back, pick one, put it back, pick one, put it back. And Python's got something out the box to do that. Sample or choice. You can do similar thing in C++. So we've seen the shuffle. If I randomly shuffle things, then I can just pick the first 3 out. Shuffled, pick 3. Good? Not sure? If I spend ages shuffling things, if there are lots of them, that's a bit over the top to just pick 3 without replacement. Those are blog posts out there about, oh, you put it on an unordered set and use an index, but if you've got repeats, then a set is going to lose the repeats on things. Good news, there's now a standard sample as well. So the moral of this story is things change, and if you're trying to do something like sampling or picking one or doing the replacement, and you're not quite sure how to do it, you never know, it might have been introduced to the library and you didn't notice. So try and keep your knowledge up to date. Do look back. Things are changing and making our life easier and harder at the same time. We like it, C++. There's some depth behind that, but we're running out of time, so let's not go there. If you want to choose one thing of many, there's discrete distribution. And by taking 1 over the number of things, I've made all of them equally likely, that gives us a way of just picking 1 and then putting it back. But that means you can easily weight things as well, and that's the thing you might want to do if you wanted to simulate unfair coin toss that is twice as likely to get heads. That's the go-to thing. How do we test things? I think we frequently end up with testing the properties of the random number generators rather than our code, which is a terrible idea. So we've talked about seeds and possibly having to rebase things if we upgrade compilers, which is fine. Lots of times, if you set your code up so as you're using a lambda or something like that, or just send in some kind of invocable to a function, when you test it, if you just send in 0 every time, you ought to be able to work out in your head what's going to happen next. And I found lots of bugs in some mathsy, financy libraries because you've got all this complicated maths But if you end up multiplying something by some random number, loads of it just drops down to 0, and you can work out in your head what you expect to come out. So that's quite a good starting point, as long as you've got a way of sending numbers into functions. If your function calls out to a random number inside, you've made your life difficult. So it's almost always better to either pass in the number to the maths bit so you can check the maths, or the game you're writing, or send in a lambda and then you can do the for real, not actually random, as we're none the wiser as to what random means yet thing. Or just always send in 0 or positive numbers. We've talked about seeds loads. But basically when you're testing, you're trying to test whether your code does the right things with the numbers you give it. So it's frequently worth, like I said, just sending the random number into the maths function, because then you've got single concerns going on in things. Let's just zoom over these. I picked a few Stack Overflow questions and was going to discuss those, but we're running out of time. I couldn't find any Stack Overflow questions where people were saying, how do I test this in C++? So either C++ people don't test their code, don't ask about testing their code, or we all know exactly what we're doing. Feel like you know exactly what you're doing? If you have got some tests, you can do things like just running them in random order. That flushes out some bugs really quite easily. Or you can move on to, I don't know if anyone went to Phil Nash's talk the other day, but he was talking about property-based testing. And there's some things where you're not quite sure what you want to happen. And it might be okay to leave some random shuffles or something like that in your code. But you can look at the properties of what's going on. If you were simulating rolling a dice, you could perhaps check you got the numbers 1 to 6. But if you've called your code right, you shouldn't need to. It's a fine line between testing the random number generator library that you're using and testing your code. But have a think about what you're testing. And just by moving around where the numbers are generated and sending them in, you can make your life easier. Now we've just done like cards or dice, so we've had whole numbers and they've been equally likely. We've not really looked at doubles or continuous distributions. We mentioned like weighted distributions on the way through. And if you were to start getting into like random things in space, then trying to come out of a random angle on a dartboard or some geophysics stuff is mind-boggling. And we've got, 5 minutes left, so let's not do that. The distribution is just bucketing things up for us so we don't have to remember the maths formula. If you roll a dice, you want approximately 1 in 6, so eventually you'd get the oranges, but you might get the blues. And the more you do, the more likely things are to even off to what you expect. Normal distribution will give you whole numbers, and you use that to model people's heights and things, and you get most things around the middle and fewer things at the edge. And that's smeared out, so the distribution's smearing things out with maths. The generator's doing this, definitely not random, precisely defined sequence, which might be surprising if you don't know what it's up to. Which means we've got time for a race. See, this is why we care about random numbers. The green blobs all did the same thing. This time, the green blobs all did the same thing. The cyan blobs are picking a random number, a whole number. It's a number of steps. They're always going to go forward a little or a lot. And the magenta ones are using the normal distribution. So they're more likely to do the same number of steps as the green, but they might do more, or they might go backwards. If I can find the mouse pointer. And they're off. looking like we've given the normal distribution ones a slight advantage, but oh no, one of them came first and one of them came last. But I mean, on average, they all had a fair chance. But if I were to run loads of demos, we would expect something different to happen every time if I've paid attention and seeded things properly. Yeah, so we're just down to 5 minutes left. I talked about testing the random number generators, and there's some formal tests for that. One of the early ones was called Die Hard. Some joke about dice, I guess. There's Die Harder and other things. There's lots of statistical things going on in there, but even if you do statistics like the chi-squared test, the ones on the left are that you could predict where the next ones are going to happen. So that's plotting one number against the previous number. And that's quite a simple thing to do for any random number generation sort of thing. And the spectral tests give us a way of doing that algorithmically without just looking at what happens. And there's a random.org website that I guess intuitively you can see the one on the left looks random, whereas the one on the right's got some lines going through it. Still don't know what random means, but there's a battery of tests. Whether they define random for you or not, I don't know. We've not got time to talk about crypto pseudo-random numbers, so cryptographically secure. The internet tends to say things like use OS entropy to seed your class, but we can use OS entropy with random device to seed our pseudo-random classes. All I'll tell you now is they do dizzy things like x squared and some other magic, and it's a huge topic. We didn't define what entropy meant. There's some maths behind this. It's a way of saying how surprising an outcome is. Perhaps surprising or uncertain is better than random, or I can't spot a pattern. Can plug through and get a numeric value between 0 and 1. What it's really doing is kind of telling us if I can compress this down to a pattern. So if you use WinZip or other zip programs are available, if you can compress something more, then it's less unpredictable. If I can compress it right down, then it's very predictable. It might be a file full of zeros. Compress that loads. So maybe something about compression, or can I encode this as a pattern? And there's an idea called conglomerate complexity, which gives you a way of measuring how easily you can encode the pattern that you can see. And this maybe is more what we should be talking about if we want to define what random really is. But the important thing is that we've managed to code our way out of a paper bag, answer the two questions. Cryptographically secure things go wrong in loads and loads of ways, and it's quite interesting to read up on if you want. So there's some links in the slides for another time. There's people trying to use quantum computing to generate truly unpredictable numbers. That's why I ended up writing the talk. I've been reading the book, Does God Play Dice? So Einstein was like, I believe that decay of radioactive materials is random, because I don't think anything in physics can be random. Maybe we just don't know the initial conditions enough, which now feels like the chaos thing we touched on. Can anything really be random? Well, I refuse to answer that question because I can't define random. I'll try and define random first. And we're kind of out of time, really. Time for one more demo. I'm going to add some jumpers here. So, same deal as before, but now we've got some blue ones. And they can cheat. Every now and again they go, puh, boom. I'm going to barge ahead. Who's going to win this time? The greens are just doing their thing. They've all got the same average apart from the blues. They've got a chance to jump. Can you see one jumping? Oh, there we go. And I think one of the cyan magenta ones just went backwards and all safely out of a paper bag. And I think on that note, we're done. just say, I wrote a book ages ago. There's a machine learning conference going on downstairs, so perhaps we should gate crash that and ask them probing questions about random numbers. Loads of machine learning and AI stuff. The core of it is a for loop doing something random that just tries to nudge left or right a bit to get better. If you can't remember how to do any C++ and you want some practice with some random numbers and other things, I'm writing a book for Manning. It's gone on a production run as we speak. There's a discount code there which you can use to buy other books from Manning instead. And that's not got a time limit on, so share it around your friends if you want. And we've got 0 seconds for questions. Or possibly if some minutes until they want the room for someone else. Anyone want? No questions.
That means everybody can ask questions.
Or nobody need, anyone want to say anything, ask anything, run away? Well, one over there.
Yeah, so the question now is for big random numbers. So all of our seed-based generators we've seen have some kind of modulo that defines the max amount of randomness we can reach within each step. And if I now need to extend for, I don't know, int64 size random number, do I need to create my own generator, or can I somehow use these pseudo-random number generators to concatenate multiple random numbers to one big one?
I am sure that theoretically you could concatenate things. I'm sure if I tried it, I'd get things wrong the first few times. The Mersenne twister, the default one is 32-bit, but the second parameter, you can request 64-bit. I think you can ask it for 128, but you're going to hit. It depends on your compiler at that point. But certainly the Mersenne twister, the second parameter you say is 32 by default, but you can definitely try bigger numbers. But at some point, theoretically, then you'll want even bigger numbers, possibly. But some of the stuff in the library, you can ask for 64-bit values, and possibly larger ones, not that I've tried doing that. Yeah, I mean, if you start combining things, like, go carefully and make sure you've got some tests around it. No, that's it. I'm going to play with that, but I'm not sure. But you can. It's not just 32-bit stuff. You can get 64-bit stuff and possibly bigger stuff out of the box. Definitely.
Okay, thanks.
And on. Oh, there's one at the front.
Sorry, more a comment. Back in the day when we had 8-bit computers.
You lucky person.
Yeah, I remember you'd write games with 1K of memory, and of course you'd have to use the random number generator to generate the layout of everywhere, and you had to have the same seed every time so that you'd have the same rooms and the same monsters and all this kind of stuff. So they were great.
Yeah, no, I got into computing on programming on a BBC Model B, like Pac-Man, and then tinkering with the code. I gave myself 100 lives and things, but just simple random things. Even if it's not random, we never get 7 out the first time. You can have some fun with this, so go have fun. But like, if the same thing keeps happening, you probably forgot to seed your random number. If you never get a 6, or you accidentally get a 7 when you're rolling your dice, you forgot that other question about the bounds, and that's it really. But test your code. That's me done.